Hi, my name is Qinlei Ji, and I will present our work on omnidirectional working of a quadruped robot enabled by compressible tendon-driven soft actuators. We are a team focusing on soft robotic research from KTH Royal Institute of Technology in Sweden. Our work is based on a quadruped robotic platform that uses 4 soft continuum actuators as its 4 legs. The robot is developed in another study, and the reason that the robot uses the continuum actuators as the legs is to make advantage of the high degree of freedom and the compliance this kind of actuators can provide. Compared with the rigid legs, the soft continuum actuators can enable the robot to have more free motion and achieve complex movements. The robot is also embedded with IMU sensors to measure its altitude and TOF sensors to detect its distance to the surroundings. The continuum actuator has a flexible core and 3 tendons whose positions are constrained by the hard disks that are distributed evenly along the flexible core. The deformation is driven by the 3 tendons controlled by servo motors. With the cooperation of the movements of the tendons by either pulling or releasing, the actuator can deform to different directions. We define the deformed shape of the actuator with the rotational angle and the bending angle. The rotational angle refers to the direction that the actuator is bending, and the bending angle refers to how much it bends. If we assume that the flexible core is not compressible, we can then build the inverse kinematic model that can describe the relation between the actuator shape and how much each tendon should move. However, in our previous work, we concluded that the achieved motion of the robot using the gates developed by such simple model is not ideal. So in this study, we further enhanced the kinematic model by adding the compression motion to the actuator. The compression can be realized by pulling the 3 tendons with the same amount. We can then enhance our previous model by simply adding the compressed amount to each tendon. We first validated our new model with the actuator simulator that is developed using MATLAB Simulink multi-body module. The Simulink model can simulate the deformation of the actuator as well as how much energy is consumed by the servo motors. The proposed model shows very low shape estimation error compared with the simulation results in terms of rotational angle, the bending angle, and the foot height. We then developed a simple throat gate using the previous model. By assuming that the legs will swing forward and backward with the same amount, and also defining the amount of the maximum compression, we can acquire how the 3 tendons should move for each leg. Same as before, we validated the movements of the feet in simulation. We can see from the animation that with the compressed amount, the foot of each leg is supposed to touch the ground when the leg swings backward, and then remain in the air when the leg swings forward. With this motion, we hope to create the forward motion for the robot. We also need to assume that the 4 legs swing in the same plane, and the swing direction of the 4 legs also refers to the direction of robot moving. We first validated in simulation how the different parameters of the throat gate, including the swing angle and the compression amount, affect the robot walking performance, like the walking speed and the cost of transportation. We can see that larger compression lengths lead to larger walking speeds for the same swing angle. When the compression is too small, the cost of transportation can also become larger for larger swing angles. Thus, we can choose an optimal compression length that is around 5 to 6 millimeters, which can minimize the overall cost of transportation. We can also change the speed of walking by only tuning the swing angles. If we observe from the top of the robot, we can see that the robot is not walking straightly. This means that our previous assumption that the robot will walk in the leg swinging direction is not accurate. Thus, we further added the 2 separate closed-loop control to regulate the speed and walking direction to the reference values. We tuned the controller parameters in simulation, and we can see that the direction and the speed of the robot are automatically corrected by the two controllers. Finally, we validated our results on the real robot. Due to the closed-loop control, the robots are resistant to the external disturbances and can follow the desired path in any direction. Furthermore, due to the free bending of the robot of the four legs, the robot can move in any direction without the need to change its body directions. If we keep changing the direction of walking, we can also enable the robot to perform more complex motions, like performing a sharp turn. This can enable the robot to have better mobility in constrained moving spaces. At last, I would like to play a short demonstration video that concludes our study. That's the end of my presentation. Thank you.